Hello everyone, welcome to my next session on System Verilog. So in this we will discuss about semaphores and mailbox, which are critical synchronization mechanisms in System Verilog. So semaphore control access to a shared resource and mailbox enable data exchange between the processes. So let's understand both of them in detail. This is the agenda for today's session. So I have structured it in a way to cover everything you need to know about semaphores and mailboxes. So firstly, we will start with an introduction to semaphores and its importance in resource management. Then we will discuss its methods and understand it with few examples. After that, we will shift to an introduction to mailbox, explore its types, and cover its methods along with few examples. And finally, we will wrap up with an assignment to test your understanding. So let's start with Semaphore. Semaphore is a built-in class in the std package of System Verilog, and it is designed to manage the resources. So it controls access to a shared resource. Say for example, you have multiple threads running in the system and all of them want to access the same resource. Then they can use a semaphore to get access, otherwise the race conditions will happen. So a semaphore is like a key that ensures only one thread uses a resource at a time. And conceptually, it is like a bucket with a fixed number of keys. So process must take a key from this bucket to proceed. Say for example, if two keys are available, then two threads can can take the keys from the bucket and use that resource. And once the process finishes, it must return the key back to the bucket. If no keys are available, then the process must wait until keys are returned back to the bucket. So semaphore basically helps in manage the resource sharing and thus helps in preventing the race conditions. So now let's walk through the key semaphore methods which you need to know. So first one is the new. New is the constructor method which is used to create a semaphore with specified number of keys. Say for example, if you are creating a semaphore with two keys, it means two processes can access the shared resource concurrently. The syntax of using this is semaphore name equals to, you are calling the new and passing argument which would be the key count, number of keys which you want to create. Next function is getIn. This is used to acquire keys from the semaphore. So by default, it tries to get one key, and if keys are not available, then the process waits until the required number of keys become available. Example is this. Next we have putIn method. So this method returns the keys back to the semaphore. So once a process is done using the resource, it calls put to release the keys. And by default, default value of n is one key, means if you do not pass any argument, it would release only one key. The syntax is like this. Finally, we have try-get method. So it is a non-blocking version of getIn. So in case of getIn, if you are calling this function with argument value as 1, and if keys are not available, then it would wait until the required number of keys are available. But in case of try-get, if the requested number of keys are available, it takes them and returns 1. But say if keys are not available, then it won't wait. It simply returns 0 and moves on without waiting. So this is useful when you don't want your thread to wait. So now let's understand the usage of semaphore and how it works in System Verilog. So this is a practical example of semaphore. Here we are creating a semaphore object with just one key by using this statement. So this means that only one process can acquire the token at any time. In the initial block, we immediately acquire the key using the statement sem.get1. So this process has already acquired the key. So now semaphore has 0 keys available because we created the semaphore with only one key. Now in the fork join construct, we are launching two processes, first inside this beginEnt and another inside this beginEnt. So inside the first process, we are trying to get the key using try-get statement. But since there are no keys left with the semaphore, the process fails and it displays process 1 failed. Because we have used the try get method, it won't wait for the key to become available. It simply returns 0 and display this statement process 1 failed. And now in the second process also we are using this try get statement, and because the keys are not available, again it fails due to unavailability of keys. So the output would be the process 2 failed. Now outside this fork join, after a delay of 5 time units, we are returning the token, we are returning the key back to the semaphore. But by this time, both processes have already executed and moved on because try get is non-blocking. So it means if a process cannot get the token using try get, it won't wait. And if we had used get instead of try get, then the processes would have waited for the keys to become available. So this is a very good example to understand the difference between blocking and non-blocking semaphore methods. So now let's take another example to understand how semaphores manage resources among multiple processes. So here in this example, we are creating a semaphore with two tokens. Means two processes can access the shared resource simultaneously. Then we are defining a task. Inside this task, we are first printing the waiting message. Then we are acquiring keys from the semaphore. We are acquiring only one key at a time. Then we are displaying this message got token, and after a delay of 10 time units we are displaying the message done, and then we are releasing the key back to the semaphore. In the initial end block we are using fork join construct, and it would run all the statements inside the fork join construct in parallel. So all the three tasks with value x, argument value as y, or argument value as z, they all would run in parallel. So when all will begin execution at timestamp 0, so it would print at timestamp 0 x waiting, at timestamp 0 y waiting, and at timestamp 0 z waiting. Next, they try to get a key from the semaphore. But we have created the semaphore with only two keys. So say x and z get the tokens immediately and they begin execution. So now we have printed this statement at timestamp 0 x got token, and at timestamp 0 y got token. But the third one z has to wait until one of the tokens is released. Now after 10 time units, either x or y completes and it would return the key back to the semaphore. And after that z can start. So now after 10 time units, z got the token, and then after 10 time units the z would print the messages done. So this behavior ensures that only two processes run concurrently at any point, even though all three were launched at the same time. So this is another example of semaphore. So here in this example, we are creating semaphore with 0 tokens. It means no process can acquire a token immediately. So inside initial block, we are using fork join construct, and inside fork join, we are initiating two processes in parallel. So the first process starts immediately and prints T1 waiting. And after that, it tries to get a token from the semaphore. But since there are no tokens, so it blocks and waits. Now the next process starts. After a delay of 5 time units, it prints T2 waiting. And then it also tries to get a token from the semaphore, and it also blocks because no tokens are available. So the output of this program would be T1 waiting. After a delay of 5 time units, it would print T2 waiting. And after these messages, the simulation will halt because both processes are waiting indefinitely for a token that will never become available because we are not creating it. Now this is another example of semaphore where a process tries to acquire more tokens than available in a sequence. So here in this example, the semaphore is initialized with only one token. Inside the initial block, we are trying to acquire the token. Since we have one token available, so a token is acquired here. Now there are no tokens available in the bucket. In the second statement, we are trying to acquire another token. But since no token available, so it blocks and waits indefinitely here. So the statement, this goat second token is never reached. So the simulator will hang here with no output unless this first process puts a token back using the put statement. So if you exhaust the available tokens and try to acquire more without releasing them first, so your simulation will hang. Now let's move to an assignment based on Semaphore. So for this assignment, you need to imagine a four-way traffic intersection where each of the four-way has a car and it is trying to enter. But only one car should be allowed in the intersection at a time. So for this assignment, you will use a semaphore with a single key, and each car must acquire the key before entering and release it upon exit. You can use $random to simulate arrival times. Finally, your simulation should log when each car enters and exits the intersection. So this assignment gives you very good understanding on synchronization and mutual exclusion. Now let's move to Mailbox. So Mailbox is a built-in System Verilog class that allows one process to send data and another process to receive it. So it is just like posting and collecting a letter from a physical mailbox. So it is very ideal for synchronization and communication between parallel processes. So there are two types of mailboxes based on the type of data. Typeless mailboxes where any type of data can be stored. And typed mailboxes, they are restricted to storing a specific type of data. Similarly, based on the size, mailbox can be bounded or unbounded. And most importantly, mailbox operations follow FIFO order, first in, first out, means data is retrieved in the exact order it was sent. These are the types of mailboxes available in System Verilog. So at the top level, all mailboxes fall into one of two categories, either typeless or typed. Now each of these can further classified based on size. They can be bounded or unbounded. So overall we have four types: typeless bounded, typeless unbounded, typed bounded and typed unbounded. So this classification helps us in choosing the right mailbox depending on the application need. So now we will explore its syntax and examples for all of these types. Now let's understand the key differences between typeless and typed mailboxes. So typeless mailbox, they are also called as generic mailbox, and they can hold data of any type. Means any kind of data can be stored and retrieved. So this gives flexibility, but it comes with a risk. So here retriever of the data must ensure that it is retrieved as the same type in which it was stored. So sender and receiver must coordinate carefully. And if receiver tries to cast it incorrectly, then this check is done at runtime. So syntax is simple: mailbox and the mailbox name. And by default, all mailboxes are typeless unless specified. Next, we have typed mailbox. They're also called parameterized mailbox, and they can transfer data of specific type only. Means whatever type of data you stored, you can retrieve only same type of data. And the syntax is mailbox and the type and the specified type and the mailbox name. So here if you try to retrieve different type of data, then this check is done at compile time. So in short, use typeless when you need flexibility, and use type when you are looking for safety and clarity. Now let's understand bounded and unbounded mailboxes. So bounded mailbox, it has a fixed capacity. That means it can hold only a specific number of messages at a time. And we create it by using mailbox name, and new and size. So here size defines the maximum number of messages it can hold. So once this mailbox is full, and if you try to put more data into it, the process will be blocked and it will wait until space becomes available. So next we have unbounded mailbox. It has no size limit, means it can store any number of messages. So it never blocks when you try to put a data into this type of mailbox. And it is declared by using this syntax. Since there is no upper limit, so you don't have to worry about the capacity of the mailbox. So you will prefer the unbounded mailboxes when you want non-blocking behavior without worrying about the limits. So these are some of the methods provided by System Verilog mailboxes. First we have new. So this method is used to create a mailbox. If we pass an argument n, it creates a bounded mailbox of size n. And if we do not pass any argument, then it becomes an unbounded mailbox. For example, here in this case, we are creating a typeless bounded mailbox of size 2. Next we have num. So this method returns the number of messages currently present in the mailbox. And the syntax for using this method is this. Next we have put operation. So this is used to put data into the mailbox, and data is put into the mailbox in FIFO order, first in first out. If the mailbox is bounded and it is full, the process will block until space is available. And the syntax for using this method is this. Next we have try put. This is a non-blocking version of put. So it tries to put data into the mailbox. If successful, it returns 1. If the mailbox is full, then it returns 0 without blocking the process. So this is a syntax for using the try put method. So these methods give us precise control over how data is managed and synchronized between different threads in System Verilog. So next we have get method. So this method is used to retrieve data from the mailbox. If the mailbox is empty, this method will block until data becomes available. Next we have try get. This is a non-blocking version of get. Means it also tries to retrieve data from the mailbox. If it is available, it retrieves the data and returns 1. But if data is not available or if the mailbox is empty, then it does not block and returns simply with value 0. Next we have peek. This method copies the data from the mailbox without removing it. And it is a blocking task, means if mailbox is empty, then it will wait. Next we have try peek. So similar to peek, this method copies the message, copies the data from the mailbox without removing it, but it is non-blocking, means if the mailbox is empty, it simply returns with value 0, and if the data is available, it copies the data and return with value 1. Now let's understand a System Verilog example for parameterized unbounded mailbox. So here in this example, firstly we are declaring a mailbox of integers, means it can only hold integer data. Next we are creating unbounded mailbox, means it has no size limit. Next we are using a fork join construct to simulate concurrent execution. So here inside this we are putting a value 10 inside this mailbox. MBX is the mailbox name and we are using a put method for putting a value 10 into the mailbox. And the consumer here retrieving the value using this get method. So the producer puts the value and the consumer gets it immediately and we get this output. So this demonstrates the FIFO behavior and synchronization using a mailbox. Now this is another System Verilog example for parameterized bounded mailboxes. So here again we are creating mailbox for integers and it is bounded of size 1, means it can hold only one message at a time. Inside the fork join construct we have two parallel processes. First process is trying to insert values in the mailbox and second process is trying to retrieve the values from the mailbox. So here in the first process, producer is first putting the value 1 and then it is trying to put the value 2. But since the size of the mailbox is only 1, So it can hold only one value, and the second statement will block until there is a space available in the mailbox. And the parallelly, in the second process, at the delay of 5 time units, this consumer will try to retrieve the value from the mailbox, and it will retrieve the value. And then the next statement for retrieving the value, it will block because the mailbox is empty now. But at the same time, this statement will be unblock because the space is available in the mailbox and the producer can put the second values in the mailbox. So you can see the coordination between the producer and the consumer, and this is possible only because of the blocking behavior of get and put. So next we have an assignment based on mailboxes to test your understanding on this topic. So here you have to create a bounded mailbox buffer of size 3. So in this you have to create two producer processes that will generate the data and try to place it into the mailbox with some randomized delay. And at the same time, two consumer processes will fetch the data from the mailbox and process it. Also, you have to display the producer ID, the value inserted, and the consumer ID along with the value consumed. So after completing this assignment, you will get very good understanding of synchronization, especially when multiple threads share a common resource. If you have any questions or need clarifications on this topic, please send me an email on the mentioned email ID or connect me via LinkedIn. Thank you.